Okay, so we're here to talk about section 6.2, the normal model. Last section, we were talking about probability distribution functions and some models and the area under the curve corresponding to the probability. So the normal model is pretty much one of the most frequently used models. You'll probably recognize it. It's the bell-shaped curve we're familiar with. And so we're going to introduce some key features of it. So let's take a look at the sample distribution. So we're looking at the actual data, the histogram here, of the mother's heights that we were looking at in the last section. And of course, we always want to comment on our center, our shape, and our spread. So we might note that our shape, I can't get it all on my screen here, but you have it in front of you, is unimodal. And symmetric. Key features that we're going to be looking at. Our center, I'm going to scroll down, and our spread. So our spread, let's see here. So our center, it looks to be about in here, maybe at like 62 inches. And our spread, one way we can do it is take our range. So our range from here to here is about 16 inches. And the empirical rule says that, right, that 3 standard deviations this way and 3 standard deviations that way, we're going to have about 100% of our data in there. So if we divide this by 6, we're going to get an estimate for our standard deviation, which is 2.67. That's an estimate. We're going to see the actual standard deviation below. So those are some things that we can just quickly comment on, and now we can look a little bit more closely. So what's the best model for a distribution that looks like this? So as I said, this is a very common distribution shape to see. So we're going to need a model that's unimodal symmetric and that has the same center and spread. So it turns out that our normal model that we're going to be using pretty much, for the rest of the semester fits this data pretty well. You can see the normal model that is this red line. I'm just trying to highlight it. It has this very distinct shape. So notice how it's curved up there, and then eventually it switches over to being like kind of curved down and curved up again. It fits pretty closely if you think about the area under the red line to the area under the blue. They're going to correspond pretty well. And we would say that this is normal if we were using our notation for a normal model. So we use the N for normal. And the first thing we would do to tell specifically what model we're using is we put the mean in here. Normal mean is 62 point, let's round to 5, and our standard deviation is 2.4. So our estimates above, when we first looked at it, were right pretty good. So it's typical to write our normal, and we write our mean, comma, our standard deviation. So that's what I did above. Another way to think about this is using our symbols. So we have the symbol mu for our mean and sigma for our standard deviation. So we're going to be seeing those things as we go along here. The normal model is the most widely used probability model for continuous numerical variables. Let's take a look at the key features. So we've seen a couple of things. Unimodal, symmetric, it has that bell shape. The mean and standard deviation are the two things that distinguish one normal model from another normal model. So the mean is at the center. So if your mean's 5, then the normal model is going to be centered on 5. If your mean's 100, the normal model is centered on 100. In our case, the mean was 62.5. Okay, and then it's the balancing point, and we said that mu is used for mean. Standard deviation measures the spread of the probability distribution, and that's sigma. I had talked about already, this is the normal notation for describing the normal model. We could say it's also called the normal curve, the normal distribution, the Gaussian model. The normal model represents the distribution of probabilities for many real-life continuous numerical variables. So this is, as I said, most commonly used model. And we're going to be able to find the probability of things because they're going to be represented by the area under the curve. And we're going to be able to talk about how to find the area under the curve, even though this isn't necessarily a simple looking curve. So let's look at our model. Note the following. Our mean is here. And when we draw our normal models, we're going to be very careful about, first, we're going to make sure we draw this nice shape. So for example, this is not a normal model. So notice that when I sketch a normal model, I'm going to be curved up and curved down. These tails are going to come really close to the edge of the axes. I'm always going to be putting my mean right smack dab in the middle, and then I'll be going along and labeling one standard deviation up. So this is like one standard deviation away from the mean. 2 standards is at 67.3. 3 standard deviations, 69.7. So this is a model of our data. It's not our actual data. We also can go the other way, down 1 standard deviation, down 2, and down 3. And so when we draw, which we will be drawing normal models, these are the key features we want. We also always want to kind of label what we're working with. So how well does this normal model do for the distribution of mother's heights? If this model is a good fit for the data, then the area under the model should also give us a good prediction of the areas under the histogram. So now we're just going to take a quick reminder that back in chapter 3, we learned how to standardize the values in a unimodal symmetric distribution. So remember, we talked about z-scores in chapter 3. This is a formula that I said that we should remember, and we're going to be using it again for the rest of the semester. So we have what we're observing minus our mean divided by our standard deviation. So if we, just a refresher to find the z-score of a woman's height of 64.9, that's what I'm observing, 64.9. We're going to subtract the mean, 62.5, and divide by the standard deviation. So this is 1 standard deviation above the mean. Because it's positive, I know it's above the mean. So if we shaded in the area under the model that represents the probability of randomly selecting a woman that's less than 64.9. So here's my 64.9. We're talking about less, so I'm shading in all the area to the left. We could use some stuff we know already about the empirical rule. Remember the empirical rule states that if the distribution is unimodal and symmetric, then approximately 68% should fall within 1 standard deviation. So if we think about that, green, this is 1 standard deviation. So we're saying 68% falls in this area here. Okay, so we want the 68%. But we're also still talking about this area over further to the left. And so out here in this little tail part, if 68% in this region in here, right, then 16% out here and 16% out here. Remember, it's symmetric, so it's going to divide what's left, 32%, exactly in half. So use the empirical rule to estimate the proportion of the total area that's shaded. So I'm going to go back to the red because we were talking about the red area. So the probability that x is less than 64.9 is going to be about 16% plus 68%, which gives us about 84%. Now let's compare this to the actual data. What's the probability that a randomly selected woman is less than 64.9 inches tall? So on our table, we're going to be looking at this, right? And so we're talking about adding up 0.141 plus 0.176, and we get did I write that right? Oh, yeah, that's fine. 7.1, sorry. We get about 86 or 85.7%. So that's pretty close to what we estimated. Remember, the model was 84%, and the actual data we're saying is 85.7%. So our model's pretty good. It turns out that we don't need to refer to the values in our distribution in the units which they're measured, like inches. We can refer to them in standard units. In other words, we can always standardize the normal model and use z-scores, and that will make it easier for us to find these probabilities. So in other words, the probability that a randomly selected woman is less than 64.9 is the same as the probability that a randomly selected woman is less than 1 standard deviation above the mean. Okay, so in notation, we're talking about the probability of observing X being less than 64.9 is going to be equal to the probability that Z, our Z-score, is less than 1. So those two things are going to be the same thing. So this model here shown is our standard normal model. And the mean is 0, we can see here, and the standard deviation is 1. So we write the standard normal model is normal 0, 1. And where are you going to use that? Again, for a lot of things. So to find the exact area under a normal model, it requires some calculus. And we'll use the standard normal. So in our class, we won't be doing that. So we'll be using these probability tables. Then they're included in your packet at the back of your packet. A little cutout of it is right here. But if you go to, oops, I didn't mean to do that. If you go to the back of your packet, page 125, this is the table that was cut out to put on that page. So this is the table that you need to be able to use. It's going to be required to be used on the test. You can also use StatCrunch, and I'll show you both ways, but definitely for the test, you need this table. So let's hop back to where we were in the notes. So below is a portion of the table that I told you. It's in the back of your textbook and the back of your packet and will be included on the test. It represents these interior numbers inside here represent areas under the curve and probabilities. The margin numbers are going to give us our z-scores. So just a minute ago, we calculated the z-score that we were interested in finding was the probability that z was less than 1, right? The probability that z was less than 1. To find a z-score of 1 on our table, first we're going to come to this column and look for 1. This is really looking up the z-score. We're going to be looking up the z-score that's less than 1.00 because our table always goes out to hundredths. So 1.0, that's this much. And this last 0, the hundredth spot, is going to come from up here. And so we're going to find the one that we're exactly interested in, which is 84.13%. So our table says that the exact area on to the left of this is, so it always is giving us our areas to the left or less than. If we wanted to find the probability that z was less than 1.18, we can do that on this table too. So we're going to use our z-score. Let me switch colors to blue. So 1.1, that didn't switch now, did it? 1.1, that's this part here. And to find the 8, we need to come across the top to the 8, we're in the 100th spot. Okay. And then we come down to find the number that's in the right column. So we have 0.8810. So the probability that z is less than 1.18 is 0.8810. So that's just another example to work with. So this is part 1 of our 6.2 video, and I'm going to continue with this video in part 2. We have a few more pages left to do, but I need to make a second video for it. So be sure that you continue to watch the next video.